Yeah, hello again and welcome to the presentation of our paper BPMN extensions for modeling continuous processes. So as for a quick introduction to the motivation behind this topic, discrete and continuous processes differ in many ways, such as, for example, the identification of system outputs, the handling of termination and interrupts, and of course as well assigning inputs to the received outputs of the processes. Basically, continuous processes are characterized by a continuous process flow. Discrete processes, such as known from manufacturing and also batch processes from chemical engineering, have already been subject of different scientific publications, but not continuous processes, which are known from, for example, oil and gas industry. For this reason, we have examined the representation of continuous processes using BPMN and defined a set of requirements, which are derived from real-world scenarios. These requirements are, first of all, continuity. This needs to be depicted in a process model in order to show, of course, the characteristic flow of the process. Then we have break conditions in order to be able to define when a continuous process is changed or it is finally cancelled. As time is also an elemental parameter in such processes, we need to introduce a requirement for real-time conditions. And after this, we have also parallelism, because in most cases we have several tasks which are processed in parallel in a continuous process. Then we have exception handling for undesired or unusual process conditions. And finally, the last requirement is limited complexity, because with all the listed details coming together in one process model, which also consists of multiple tasks, for example, or maybe also sub-processes, the models need to have a level of complexity as low as possible. As a further conclusion to these requirements and results of our work, we defined BPMN extensions in order to simplify the representation of continuous processes. Here, as an example, you see a control process for drives of a machine tool on the left with regular BPMN, but also with fewer details, and on the right with our suggested extensions, but with more details. Among the extensions, we have the closed loop subsystem gateway, which is a combination of a loop and a parallel gateway. And it may have multiple branches, each one starting with one newly introduced event type, measuring, control, or cancel. As soon as cancel conditions evaluates, as a cancel condition evaluates true, a cleanup routine may run and the loop finishes. There are two features which can be defined for a closed loop subsystem, and both have two options to select from. The first is interval duration overrun, which defines what happens as soon as the defined interval for one cycle is exceeded. The second one is measure control cycle execution, and this defines whether measure and control tasks are being processed sequentially or in parallel. The suggested intermediate catching events are measuring, control, and cancel, and each depicting one important type of tasks, which are also part of processes in process and control engineering. When a branch of a closed loop subsystem starts with a measure intermediate event, the tasks after this are meant for measuring or data acquisition. And the control intermediate event works the same way for control tasks, and also the cancel event for cancellation tasks and cleanup routines. Each event condition is evaluated with every cycle. Here in this slide, you can see 3 different control processes depicted using the newly introduced extensions. On the left, we have a feedback control, and in the middle, a feed-forward control, both meant for controlling heat exchangers. And on the right, we have a cascade control, as I've already shown you before on an earlier slide. In our work, we characterize discrete and continuous processes, and we derived requirements for complete and also correct depiction of continuous processes. We applied these requirements on BPMN, and we introduced extensions in order to simplify the modeling process and also include all necessary details in the process model, while we are trying to keep the complexity of the model as low as possible. Further, we applied the extensions on process examples, which we have selected from process and control engineering. This concludes my presentation. Thank you very much. If you have any questions, please feel free to ask them.
Yes, thank you. So do we have questions from the audience? I see one. Have you considered what would be a way to simulate these process models? This is from Hugo. Question.
Yes, we are already working as a next step for our project on making these extensions also executable in the workflow engine. And it's not only a simulation, but we are also working on a small demonstrator project for a continuous process, which we could use to evaluate our extensions and see how the process models really depict the actual process. So yeah, it's a little bit of a combination between simulation and actual implementation.
Okay, thank you. Thank you. I have one question. Why do you do the extension of BPMN and not using Petri nets, for example, which are the modeling technique for all automated processes and the continuous processes usually used?
Because we are also trying to evaluate how we could display data in the workflow engine we are currently using, and this workflow engine is based on using BPMN models.
Okay.
Well, BPMN notation. Yeah.
Okay. Thank you, Diana.
Thank you.
Let's move to the second presenter. Manaz, are you here? Yeah. We don't hear you. You are muted. We don't hear you.
Okay, can you hear me? Okay.
Yes.
Today I'm going to present this 4 case level counterfactual explanation in process mining. And to motivate this work, let me introduce you John. God, it doesn't move between screens. Sorry, it now it's moved to other screen. Okay, good. Okay, let me introduce you, John. John is a good customer of ours, and John, mainly he's a good customer, but now he has some complaints. For example, he is thinking that his case took too long, or he's angry because his request get rejected. And we're going to solve this issue by explaining him that what caused this situation. And also we're going to give him some explanation in a way that he can use it in the future to not have the same unpleasant result again. Also, most importantly, we're going to do that in a way that we don't violate any privacy thing, and also we don't have any information leakage. For that, we need to give John a set of good explanations, which should be, first of all, some possible explanations. Second of all, they need to be close to the reality. They need to be simple and understandable by a human, and they need to be applicable. Applicable means that they should be somehow that the person can act on them. It is sort of case sensitive, and we need to give everyone a set of explanations, and that person can decide which one to pick. Each explanation, in fact, is a counterfactual statement. Counterfactual statement means an alternative to the past that shows John how he how he had to act differently to get different results. For that, we follow the following method. First, we enrich the event log, then we create a data table. We need the statistics of this data table, and also we need this data table to infer the structural equation model. Structural equation model is sort of a set of equations that encodes the causal relationships between the features in our data. And in this data table, one of the rows, one of the instances is about John. We call it the current instance. And now we can generate a set of explanation for John with this information. How we extract the data? First of all, we have an assumption that the recording time is negligible. So we need to extract the data from the part of the trace that happens before. A trace is a set of events about this specific case that here is John. For John, we have some, we can imagine some features, descriptive features like x1 to x9. And also X problem is the feature that capture the problem like delay. The other information that we need to have is a set of these subset of, in fact, these descriptive features should be given as the actionable features. For example, when we have a patient, we cannot change the level of severity of his or her disease, so it's not actionable. But we could assign to him or to her a different doctor. So the assignment of the doctor or the number of doctors that has been assigned to the patient is an actionable feature. With this information, we start generating a set of new instances. These instances are in fact the counterfactual instances. And how we generate them? In the instance that is about John, we replace some of the values of the actionable features. For half of them, we replace them with just random values, and in other half of the instances, counterfactual instances, we replace them with values that came from the same distribution of that feature in the data. And then we evaluate them using some or a good machine learning method to see which one of them could result in a desirable situations, desirable values, outcome. For this purpose, we highly suggest to use the structural equation model of the data, and we can see later why it is the case. This data, that these instances that I encircled in pink, they can be used as explanation, but the problem is that they may be quite far from the instance of John. Then what we can do, we can use optimization on these instances and make them as close as possible to John, to the instance of John. And also we can use the instance of John and use optimization and try to turn them to some instances that are good instances. Here, sort of the search space is the big area, and those light blue are the instances that were desirable for us. And then the set of instances, counterfactual instances that has been generated this way can be combined into a set of explanation for John. We have implemented this method and we have used it on a set of data, on a data set that has been generated using this specific structural equation model. It has 5 features, and as you can see, for example, C were 10 times the value of A plus some noise. That noise are not mentioned here. And we select one of the instances as the sort of current instance, John, and we try to find some value and with a threshold that is 500 to see how we can generate some explanation for him to get a result lower than 500. Because for him, it was 577. And as you can see in the generated examples, there is a huge difference between the value that has been generated by SAM, structural equation model, and the other very accurate learning methods, machine learning methods like neural network, local weighted learning, and regression tree. We get the structural equation model that here we have it as the ground truth. And if we consider that here it is, in fact, the ground truth, you can see that the value of other, the predicted value of other methods differ a lot from the SAM. And also the number of features that differs between them is shown in the right side. We use the same experiment for a nonlinear structural equation model, and we got the same results, almost the same results. So with this experiment, we can sort of highly suggest to use a structural equation model for predicting the value of counterfactual explanations. Thank you for your attention.
Thank you for the presentation. So if someone has a question, you can talk or you can write. I see no one for the moment. Okay. For me, this concept of this term of counterfactual is very new. So
yeah, counterfactual is a concept that, sorry, yeah, please.
So I'm trying to understand what's the difference with like analysis of variance, alternatives, like things like that.
It's sort of an alternative. It's a counterfactual comes from sort of causal theory, causal inference theory. And it means that, for example, if you say something, what if I didn't have had, for example, breakfast, what would have happened now? It's a counterfactual.
Do you have some guidance how to explore this counterfact, how to find them, this counterfactual?
There is, in fact, because we cannot imagine any linearity or any nice property, at least we try to make it as broad as possible, about the structural equation model. We sort of start with a very, very big set of samples. Sample evaluation is quite fast. We can do it in parallel, and it doesn't take time, even if the number of samples is too big. We can use a mesh kind of structure to sort of make a better estimation of our search space. But we have no other idea, no other way to do that.
Okay. Okay, let's move to the next. Hugo, you already ready? You are muted.
I know, I don't, can you unmute me?
No, I cannot. You have to unmute yourself.
Fair enough. Thank you. Okay. So, welcome again. This is Hugo Lopez and Jean-Marie Nirdizati with work with Rasmus Council and Mark McCord. And today we're presenting the classifier process discovery, this process and textual views. And basically what we've been trying to is actually go very close to what Jan was presenting yesterday, a tutorial in which you have the process, the understanding of a process, building a mental model of a process requires the understanding of different artifacts. Some of those artifacts can be the process representations, the graphical representations that we have, and some others that are textual. And they work for different purposes. Navigating, optimizing, it becomes easier in model views, but reasoning sometimes is actually easier in textual views. And we would like to build up a pipeline in order to, first of all, do discovery of process models from the text, but also to keep the link between these two artifacts at the same time. And this becomes difficult. First of all, when you're looking at process descriptions and try to build up a discovery algorithm on that, well, the standard techniques of process discovery, they don't really work because you don't really have a structured artifact like in event log. You have unstructured data, in this case, standard words that people have used in a given grammatical structure that changes from domain, that changes from author, that changes offline, and so on. So building an algorithm that is generalizable, that and can still learn what is part of the process and what is not part of the process becomes a challenge. The second part is actually what happens once you have built the model. How is the interrelation between the information that is in the model and the information that is in the text? Which part should be considered and which part should be discarded? So, to give you some examples, we have some examples of ambiguity here. Take on the left side, you have a couple of documents that we want to do mining from, and then we would like to have a resulting graph, which is the one that we have on the right. Now, what we see is that certain process elements, they have actually many-to-one correspondence. So one token, like clerk, one process element like the role clerk in the right-hand side is represented by different tokens like clerks, the clerk, and he. Similar things with events. So a claim is closed, and I'm going to close the claim. They actually represent the same semantic information, although the utterance is actually changed. Similar thing with atomic and compositional alignments. Some utterances they identify one given a process element, like in the case of activities that receives and claim works the same as receives and claim in the process model. But if you look at the constraints, rules, they actually require the composition of the aggregation of different process elements. Like a constraint that requires at least a couple of events in order to be a valid relation. So a keyword only doesn't really work. And if you move from that, then the other part is a normative versus learned interpretations. So standard process discovery techniques in text, they have normally used a normative definition. So take a keyword and assign an intended meaning to it. So a may responds to a given constraint in a declarative process model, and a must should correspond to another type of relation. However, when you see the actual meaning in process descriptions, it is not always clear cut that way. The words, they actually have a meaning depending on what is in the context. Two words on the state of the art and their shortcomings. We can divide this into basically two main approaches, either rule-based approaches or machine learning approaches. In rule-based approaches, we have some questions on how can you generalize and build up new rules for different domains, for different authors. It becomes difficult to generalize. And the second part is ambiguity. So things like the example that we're giving you here, we open the new claim, a claim and then supports the customer, can be matched into both a sequence or a parallel pattern. Similar thing with co-reference. In a co-reference, well, you have you cannot really map this into a problem. You cannot map he onto a process model until you understand what this he refers to an agent. On the other side, you have the machine learning approaches, and here we find that they can actually generalize pretty well if we have a good data set that is built for process descriptions, which at the moment is currently lacking. And that's what we try to build in this architecture.
Yes, and we have a closed framework of this process discovery, in which you input a process description, and it goes through different phases. The first one is a pre-processing phase. The second one is our discovery and reconciliation phase. It's based on two different extraction phases, a rule-based and a machine learning-based extraction. The machine learning-based extraction is from our training data, process descriptions, in which the user's input. Then it goes through the pre-trained BERT model, and we used 3 different BERT models: relation identification, relation type identification, and a named entity recognition model. Then we combine the 2 models, mainly by intersection, in which you then get outputted a process model and the annotated text. Finally, the key features of this approach: it generates declarative models and traces their relation back to the textual artifacts, and reduces the time that process models would spend mapping these processes. And it works on multiple domains. It does not need all level to near pre-training before being used. For the validation, we combined mixed data sets by 15 different process descriptions, 5 from the HTTP, 5 from Declare, and 5 our own excluded from our initial training. We define a match when there's a process linked element to the textual description, and the predictive fragment corresponds to the manual annotation. Finally, the algorithm is part of the process highlighter, the hybrid process representation tool. It combines both the text and the declarative models. It's also part of the DCR solution. It's open for testing using an academic license, and the dataset and experiment is available in GitHub. Thank you for your time.
Thank you for the presentation. So, do we have questions? More or less the same people in the room, so.
There's Serena, the raised hand.
Okay, please.
Well, I always kind of a little bit wonder what kind of business projects or consulting projects would this really be helpful to. So what often happens is that the process descriptions are quite bad and out of date, and they are especially bad and out of date concerning the activities for which there is not a lot of data either. So can you a little bit maybe elaborate, or what are your thoughts about these sort of real life problem situations where nothing is perfect? And yeah, so what's your take on this?
That is a very good question, and thank you for posing that. So for the business cases that we have, we've been mainly using this for normative processes, meaning processes that regard compliance from regulatory documents. So we use this for laws, we use them for service operating procedures, SOPs, that are not really given for one organization, but from the state, and or clinical guidelines. That's another one that we look. That's not because as you mentioned, the process evolves with time, and this is something that we also would like to look at. But we also have a normative process, and that normative process that is actually extracted from the law, and people need to follow that one. So it combines very well with a pipeline of process compliance and process conformance.